Everybody, today I will have a lectures on the lecture 10, which is about concept of stress. So before we going into the topics, I would like to rehearse you a little bit regarding what we have learned so far. So we learn about mechanics, remember, and we have static. So equilibriums, system. Also to say sigma f equal to 0, no movement. Secondly, we learn about dynamic. So there is a movement of body, and sigma f is equal to ma. In this case, we have acceleration here. So regarding today, we will starting about mechanics of materials. Also to say, we can say also concept of stress. What does it mean by mechanics of materials? So the mechanics of materials means how the structure of the body works. For example, how much you apply the force until one body is break. For example, the rod here. When you have a bar, stainless steel bar, you apply the force, and then you say what is the max force that can apply to this bar until it break. Or you have a bar, you have two force on the side here, minus F in negative. How much F max until the bar break. So to say, what we have learned so far here, we just learned about how to derive the force in the system. And next one, about this one, we will learn about real case in the in the engineering problem. Because for example, in the future, maybe you have to design. For example, you are a designer. You have to design something which have to withstand certain load. For example, you design a bridge. Okay. You have to design a bridge, for example, and then you have a car on it. So the car itself has mg. So this is the weight of the car applying on the bridge, and maybe you also have to do the calculation how much this kind of pillar can withstand this load from the car, for example. Okay, so today we will starting to get real stuff, because for example in the past couple of months, you're also wondering why we are learning about the static, why we are learning about the dynamic, how was it used in the engineering problem. So let's start. Okay, so coming back to this, so the concept of stress here, the main objective of the study of the mechanics of material is to provide the future engineer with the means of analyzing and design variant of the machine or the load of bearing of the structures. And they say this is just I'm sorry, I a little bit have a running nose. Let me wipe a little bit. Okay, so the mechanical materials, what does it mean? It means that we have to analyze the structures and analyze the material strength, analyze the material stress, and then we can derive what is the design which is how to say suitable or can withstand this kind of load. Both of the analysis and design are given structures involve the determination of the stress and deformations. This chapter is devoted to concept of the stress. So then maybe you have a question, what is a stress? You will get into more detail later, but here is the descriptions. Stress is a physical quantity that expresses the internal force the bearing particles of the continuous material exerting on each other. What does it mean? So the stress itself, maybe I go back a little bit to this pictures. So for example, I would like you to get to a big picture first before we going into the smaller pictures. What do we have here? I'm talking about on the other side, not coming from the lecture itself, because if I go from the lecture, I start with static and then it's go to dynamic, go to material, mechanics of materials, but instead I will go to the product itself at the end. Okay, first, for example, in the real problem, you have, as I say before, then what should I use as an example? So I would say I have aluminum bar, okay? I buy an aluminum bar here. And I would say this bar will have a tension force because for example, I would like to use this to attaching to the weight here. So this will become the tension force, and then here also have to attach to something, and we have also the tensions. So here we have a force applied to this aluminum bar, for example. And then I just like to ask how much of the weight that this aluminum bar can withstand. So, and then if you are engineer, where do we start here? Okay, so first you have to use the static, because in these questions it's about the static, nothing is moved, right? So we start with the static. First you have to derive what? For example, it's set to this. So you have to derive the support force. For example, find internal force. You see in the example later on the right side, it's not as simple as in this question. So you have to find the internal force. What does it mean by internal force? For example, if you have many For example, on the right side, you have some kind of this bar and the support, and then you have force. Then this red one here, what is this one? Is external force. And what is internal force? Internal force means if you have this rod, you decompose it, and how much force is applied inside this rod. Okay? Then if you can find the internal force, then we have to use the knowledge about mechanics of material. This is the first step. We use static. Second step, we have to use mechanics of material. We have to understand how the material works. So for example, in this aluminum, strength. Okay, maybe I'm not good to written here. So I will say find the load, or so to say stress of the body. This is the first step. Then find the strength. Also to say this strength, normally we find it from database of materials or testing, which in this case there will be no calculation for the strength. For example, in the near future you will see that we given the strength, and then we have to do the calculations comparing the strength and stress, and if strength more than stress, then I will say okay, the body can withstand the load, and if strength less than stress, then body break. Let's see what does it mean by this of these summaries. Okay, you see in the near problem, then I will leave this on the left side so that you can still seeing it. So first we have the structure is designed to support 30 kilonewton load. Okay, so this is kind of actual problem. For example, you have this kind of you design this kind of things. I just redraw it. Okay, and then you design this kind of thing. I write it in 3D, and then you hanging some load by, for example, 30 kilonewtons. Okay, so here's the real problem here. Okay, so I will just no. So the structure is consists of the boom is here, and the rod here is and joining by the pins, zero moment connections because it's rotatable, and the junction and the support. Also here also the pin, here also the pin. And first we have to perform the static analysis to determine the internal force in each structure member. Okay, so coming back to this, here is really the first step, static analysis. And this is what we're gonna do here. So, do you remember how to do this? This is what we have learned in static in the very first class. So first we have to define the load, the support force, okay? And I will shade it to blue. So, here, what kind of support we have on the left side? You may already seen it in the following pictures. So we have this reaction force on the x-axis, and we have a reaction force on the y-axis because it cannot move on those directions. But you can see that there is no supporting moments. The reason is because we have a pin there, so it can really rotating, and the moment is zero, as is also mentioned in here. Okay, and we considering the static equilibrium of this system. Do you remember? Still sigma f x equal to 0, sigma f y equal to 0, and sigma m equal to 0. This is our governing equation that we will use most likely in the static in the first step. Okay, so first, what would you do in this case? So for the first hint again, just take the moment at any point that has the most unknown force, right? So, okay, so you know already that here is unknown, here unknown, here unknown, and here is unknown. What should we do? So I propose we can start with the point C. So we have sigma MC equal to 0. And then what do we have here? We have only this x, ax, and we have this as a moment on that point, right? And I will write also the directions. We have this as a plus. So in this case, we have plus ax times 0.6 meters, and we have also minus 30 kilonewtons, and we have 0.8 meters here equal to 0. And when you solve this, you will get ax equal to 40 kilonewtons, and then you already know ax, so next it's easy. You have sigma fx equal to 0, and then you have ax equal to cx, which is 40 kilonewtons. Okay, oops, no, this one is negative. Why? Because we have ax plus cx equal to 0, and then it's become negative when we switch the sign. Means in this case we have to switch the direction of the Cx here, because Cx instead we have this as a negative directions of 40 kilonewtons. Okay, and then we have sigma Fy equal to 0, and in this case we have Ay equal to plus Cy and minus 30 kilonewtons equal to 0, and then in this case we have Ay plus Cy equal to 30 kilonewtons. So actually you can see that this kind of support is over constrained. Okay, so we cannot really define the force of those two, so we leave it like that. Okay, so Ay and Cy cannot be determined from these equations because we over constrain. So we have 3 equations. We should have only 3 unknowns, but in this case we have 3 unknowns here. Okay, alright, so how do we solve this then? So next, in additional, to complete these structures, each component must be satisfy the condition for the static equilibrium. So we consider the free body diagram of the boom to be sigma mb equal to 0. Okay, and then we have only Ay here, which is equal to 0, and then if we substitute into those back there equation here, equation 1 here, if Ay is equal to 0, of course, then Cy will be equal to 30. So in this case we neglected this support. Okay, so now we have all the support force, and here is all the direction of the support force along the boom and the rod. Okay, then next, what next we have to do? So we already know the support force. Okay, so I will just check on this. Actually we already have here support force. We have all 3 support force available. So next we have to, I just saw it, my mistype internal. Let me erase this. Okay. So next we have to find the internal force, and the boom and the rod have 2 members. Do you remember about the chapter that we have learned about the truss? Remember this kind of structures? I know maybe some of you don't really like to remember this, but we have this kind of stuff. For example, we apply the force on those structures, and then we have to find first, same as this one, we have to find external force, later we have to find internal force. Okay, so we just neglected this. And the boom and the rod are 2 force members, and the members are subjected to only 2 forces, because remember here is a rod, the rod and the boom here, we will have only either tension or compression. In this case, we are just assuming in these directions, okay, that we have a rod of tension and the boom of compression. But when you are doing the questions, actually you can place the direction at any, how to say, any directions, because in the end, if the direction is wrong, it will get negative sign, and then you have to switch it. Alright? For the equilibrium of the force must be parallel to the axis between the force application point, equal in the magnitude and in opposite direction. I think you have learned this already on the thrust lectures. And you know we have a joint here, so we are not having only the force, but we have a joint here also. Remember, here's a joint B, and if you can remember, this joint, it has the opposite sign of force to the rod or to the other member that is attached to. That's why you can see it here that the directions of the force here is being how to say, in the opposite side. And here is what is the force that is applied on the, here is the force which is applied on the joint B. And what do we have to find here? We have to find how many, we have to find the magnitude of FBC and FAB here, because here is the internal force. Because internal force is a force inside that acting on the rod directly, not the external load. And we have to find these internal forces, okay, for the next step. And the easy way to do this, there is multiple way. One way, you can also use the sigma f y equal to 0, sigma fx equal to 0. Those two governing equations from first law of Newton's, and then you apply this, and then you can find, you have two unknown, and then you have two equations, so you can solve this. But what you have to do is you have to a little bit using the triangles rules to decompose this vector into the x-axis and y-axis. But in this case, I will use sign rules, sign laws, just to solve this one. So if you remember, here we can use this FBC, I think it's from this one. FBC here is over 5 equal to FAB over 4 equal to 30 kilonewton over 3. And from this we know that FAB equal to 40 kilonewtons, and we know that FBC is equal to 50 kilonewton. Okay, so we have those two as our internal force. And next, can the structures safely support the 30 kilonewton load? Can it be? Let's see. So from the static analysis, we know that what we can see here is FAB, or this rod, this bloom is get compressions, and this rod get tensions. Firstly, what you have to know is the strength for compressions is much higher than the tension. What does it mean? For example, if you have kind of rod, it's required a lot of force to really compress it until it breaks. Comparing to the tension, when you pulling the rod, it's easier to break by pulling to have a tensions inside. but the compression is really required really high forces to break. So in this case, I would also really consider on the tension first. It doesn't mean I didn't care about the compression things, but first we have to take a look on the tension stuff, okay, because it's quite more severe. And okay, so at any section through the member BC in the internal force 50 kilonewton with the intensity of the stress. What does the stress mean? Stress means the force in really small area in the particles. So in this case, we have to find the stress on this rod, and the stress, the formula is easy. This one, stress equal to force over area, and in this case, this internal force is what? Is F BC, and the area is pi r square or pi d square over 4, and you have 50 kilonewtons, and then here is diameter is 20 millimeters square over by 4, and then you have to also change this millimeters to the meter stuff. So in this case is millimeters over 2. So what you have to do is you have to multiply it by 1 over 1000 square, okay, and in the end you will get 159 multiplied by 10 to the power of 6 Pascal, or you can also say 159 megapascal, okay, and this Pascal PA is equal to Newton per meter square, okay. Please be careful of the unit. So from the material properties for the steel, the allowable stress is 165 megapascal. What is the conclusion here? Is it break or not? This is our stress. The stress BC is equal to 159 megapascal, which is less than the strength of 165 megapascal. What does it mean here? So it really means that this rod will not break because the stress is less than the strength. The strength is kind of the load that it can withstand until it break, okay, but this load itself is not reached that level yet. So the conclusion is the strength of member BC is adequate, so it's sufficient. So the member can withstand the load of 30 kilonewtons. Okay. And for example, then what does it mean if, so previously we use the steel, maybe I can Google it, the price of steel compared to aluminum. Oh, okay, this is very, yeah. Oh, by the way, the aluminum is more expensive than the steel, but steel itself, it really cannot withstand, for example, the corrosions. For example, if you put the steel under the rain, you get easily rust, or we can call it in Thai snim. So this is the material degradations, but aluminum can withstand those kind of corrosive attack from the rain or from the oxygen or from the oxidations. Okay, that's why maybe they would like to select more appropriate materials for this rod. So this rod, instead of steel, they would like to change to another materials. So the reason is based on the cost and the weight, the availability, and also the corrosive resistance. So they would like to change this aluminum, this rod from steel to aluminum. But the problem is we have the aluminum have, of course, less strength than the than the steel bar. So we have the strength of 100 megapascal. Oh, then what we calculate previously, if we still have the diameter of the rod of 20 millimeters, we will get stress at 159 megapascal, and this rod has strength of only 100 megapascal, so mean stress more than strength. The rod of aluminum cannot withstand 30 kilonewton load. So this is the conclusion here. The rod cannot really withstand the load, which is mean it will break if we still only change the materials. What do we have to do? So one thing you have to can be, maybe there's 3 things you can do in this case, or 4. First one, you can 3 things. First one, you change the design. For example, as the problem here, they would like to change the diameter of the rod. Second thing, you change another material to be more strength. Or third, you reduce the weight here. Instead of 30 kilonewton, maybe you can just change it to 15 kilonewton that allow, for example. Okay, but in this case, we would like to improve this design by changing the diameter of the rod. We would like to increase it. Okay, so what we have to do here? Okay, so the question is, what is the appropriate rod diameters? Okay, so you know the load already. Okay, you know the stress equal to force over area. You know that this limit is 100 megapascal. This is your stress limit. Okay, And you also know the force, you know the limit of the stress that is allowed. So what you have to be changed is the area here. So means we have area equal to force over the stress, which is 50 kilonewtons over 100. Mega mean we have 10 to the power of 6 Pascal, and this Pascal equal to Newton per meter square. And then in the end we have 500 10 to the power of minus 6 meters square. And then you know we area is equal to pi d square over 4. And then we can say d is equal to square root 4 area over pi. And then we have 4. What is the area? We have 500 times 10 to the power of minus 6 meters square over pi. And then we have in the end 2.52 times 10 to the power of minus 2 meters. Also to say 25.2 millimeters here we have. Means if we have aluminum diameter around about 26 or more is sufficient. Okay, so conclusions. Suggested rod diameters is 26 millimeter or more to withstand the weight. Load. Okay. So then now we coming back to this, what did we do here? So I forgot to also do this. So we get internal force. Previously you can remember we got the internal force FBC, that is the force in the rod. And we say step 2, we have to use the knowledge of mechanical materials. We defining the load. The load here, it means is the stress. Okay, so we have to looking for the stress, and as you can see over here, we have here the stress of 159 megapascal. And then the strength, we have the strength given by the problem already, but normally, as I say, we normally get the strength from database. You can, for example, you can search on the internet the tensile strength or ultimate strength for the stainless steel, for the steel, for the aluminums. They have this kind of the strength available already on the database. But how do they get this from? Actually, they're doing the test itself. They have these different materials in the rod, and then they apply the force in the tension, and then they would like to find the strength of those materials. So this data normally is come from the test itself. They have standard tests also to define this. So this one we got it from already from the pump, and then we compare it the stress. As you can see here, we compare the stress and the strength. We say the stress is 159 megapascal, which is less than the strength of 165. Then it means we are falling to this case. Okay, then we are pass. But as I showed you before, okay, the slide it's not really working. Okay, it's work. As I showed you in the latest slide, if we change the material from the steel to the aluminums, we will have a problems because our strength is less than the stress itself. Okay, this is really critical. Means we have a body break or member break, but in this case we can improve the design. From this we can go to this. Okay, we can change to this by first change design. In this case we change the design, we increase the diameter of the rod. Secondly, change materials. Okay, you can also change the material. Okay, aluminum maybe not really good enough, so you change it to, for example, stainless steel or whatever itself. Thirdly, you can change specifications. So, for example, you change allowable load itself from 30 kilonewton to 10 kilonewtons. When you do the calculation again, you will see that the stress will reduce. Okay, and then you might have the strength more than the stress. So here's the overview. All right. So then here come back to first, because before we going into deep detail, I would like to show you how the real engineering problem calculated as you seen before. But here is the definition of the normal stress. For example, what is the normal stress? The normal stress is just the axial load on the member. Normal in this case means, like, you remember normal force? Normal force always perpendicular to the horizontal surface or any surface. Here also the same. The normal stress means we have the stress which is perpendicular to the plane. In this case we have the boom here. We have this kind of bar here, and then we have normal stress which is perpendicular. And then here what is the stress here? Stress is the force intensity on that section is defined by the normal stress. So here also the formula same as before. So the stress is just the force, the delta force, which is over the delta area, where the delta area is equal to 0. Means the really small force on particular area which is very small. Okay, and the normal stress at the particular point may also be not equal to the average stress, but the resultant of the stress contribution must satisfy this formula. Means this point, for example, this point and this point, the force may be not equal. Okay, but normally in this case, in our case, we simplify it as before. We just use this. We say that okay, this all the force in those particular area is equally distributed. But in this case, in usual case, doesn't mean that this force will equally distributed. You can see it in these pictures. Okay, the force on this side and the force on the middle. The middle have more forces, has more stress. Okay, means the middle have more delta forces over the delta area, more stress compared to the side. Okay, this is the, how to say, the general rules of materials. Normally we will have really high stress on the middle of the bar. Okay, and centric and eccentric loadings. If we have really eccentric loadings, means we have no moment at all, so mean we have this red bar. But actually, if for example we have this kind of curved bar, then we also introduce this moment to this stress to this area, mean we will have also not only the tension stress, we also have the bending load here. Okay, we also have the bending stress. So let's read it through. The uniform stress distribution of stress in the sections, that line of actions for the resultant of the internal force pass through the centroid of the sections. So here is the centric stuff. But uniform distribution of the stress is only possible if the concentrated of the load on the end of section of two member are applied at the section of the centroid. If the centroid is in the middle here, when you have uniform distribution, means your force has to be exactly in this middle path through the centroid of this bar. Do you remember how to find the centroid? I think you still remember from the chapter, I think chapter 6 or 7, that we find the centroid of the bodies. And this refer it, and then we call it the centric loadings here. Okay, if the load pass through the centroid. But for example, for two-phase two-force member which is eccentrically loaded, the resultant of the stress distribution in the section must yield an axial load and a moment. So here we will have not only the force, P force, but we will have also the moment, as I explained it. Okay. So the stress distribution of eccentrically loaded member cannot be uniform as symmetric. So it will not equally distributed there. Shear loadings. So then next is the shearing stress. So we have force P and P prime are applied transversely to the member of AB. So we have this member of AB, okay, this member, okay, and then we have shear force. Okay, why it's become like this? We have shear force corresponding to the internal force acting on the plane of section C, are called shear force. So we have a section C here. If the force is applied on the opposite side like this, we will have a shear force. Okay, and this shear force also introduced to shear stress in the end. Alright. Okay, so how do we define the shear force? So shear force, we always written by tau here. It's like this. Okay. Then this one also we use the similar formula. So we have force P and we also have the area. The area is this bar area. If we see it in 3D, okay? If this bar is 3D, then this is the area, right? then this is what caused the shear stress distributed, and this also cannot be assumed to be uniform. Example of the shear stress. So you know how the bolt works. So actually the bolt, what does it mean for the bolt? The bolt itself, if you're interested in deeply for the bolt, I can explain just roughly. When you're tightening the bolt here, what does it mean when you're tightening the bolt? The area here, the bolt will make a tensions, and then the bolt will elongate, and then it still elongate into the elastic zone. Means it still have the force attracted back. Means this bolt, when you tighten more, you will enlarge or you will make a tensile stress here, and for the material will try to shrink. In this case, then means the bolt will clamping this two stuff. So here we will have a force from the bolt by the bolt pretensions. And when we have bolt pretension like this, and then what we have learned previously is about the shear stress. When we apply the bolt itself, what is the function of the bolt? Normally is we use to clamping two materials or two bodies together. Okay? So in this case, you use this bolt to attach the member B and A together so that it cannot be separated. And this member A and B will have, for example, the shear force. They will have a force like this one and this one. Okay? And this kind of force introduce shear stress onto the bolt. Because when you pulling this in this directions, it will have a force acting to this bolt like this, F and F. And then this will be written here on the free body diagram like this. Okay? And then what is the shear stress? Then here is the shear stress. And this is called single shear stress because you have only shear stress on only one location on the bolt. But in this case, we have double shear stress. Okay? We have shear stress acting on two positions on the bolt. But what does it mean here? You can see that double position of the shear stress really improve. The stress mean we have less stress because now we have two areas here. So we have less stress applied to the bolt, even though we have two positions, but we have less stress. Mean double shear stress will yield or will achieving or will be able to withstand more load than single shear stress. Okay, but you can see that this one is better in terms of strength. Okay, but it actually, you can see that for double shear stress you introduce more material CD, and also you need also longer bolt. Means not good for cost. Okay, it's more expensive, easy as that, right? And lastly, we have the bearing stress in the connections. So we have also, of course, there's shear stress on the bolt, but this clamping part, this clamped part, A and B, also got the bearing stress also. And how do we calculating this? The bearing stress here is governing by the tall, the height of this area, and the depth of this area, and the force have to be divided by this area, and then we'll get the bearing stress. This is what we call bearing stress. Okay. All right, then let's stop it here, and then we will continue on the second half.